Now we look at the what has been written in the book, right? So in dynamics, right, when we study about kinematics of the motion, the potential energy mentioned in the thermofluid engineering, they are more general, but for dynamics more specific because potential energy has two components. First, due to the spring, right, and the other due to the gravitational potential energy. So if you look at the equation, um, the gravitational potential energy or potential energy that I described earlier, um, the it tells us about when we raise the body right from certain altitude to another higher altitude. So this is called the work done by gravitational forces, right? And the symbol being used is V, V and G for gravity, right? So you have to take notice about uh, the the origin for this case. Alright, there is another potential energy due to a spring. I will cover that later on. We just consider only kinetic energy and potential energy for the time. Now, in dynamics, there is many form of work, right? Um, there is what we call as work associated with weight, right? So if you look at the equations, so the way that the work associated with weight is defined. So you have the lower limits at a lower altitude and higher limit at higher altitude. Right? So you can see that we need to define the position vector in this case, right? And then this one is based on the dot product of a work. Right? Dot product work is a dot product of force with the displacement vectors, right? So the work associated with weight is minus the work by the weight work by the force, weight force, right? So the right by the what say the work done by the gravity force. Right. There are two ways to solve dynamic problems or using the energy balance or work energy equation. Right. The first one called a free body using a free body diagram, and then one using the active body diagram. So if you look at the diagram, we have the physical situation of the problem. We have a particle here uh, that subjected to force F1 and F2. It also subjected to, I think this one is a spring that always trying to pull the particle towards it, right? And this particle having a curvilinear motion from A to B, right? So when we want to use the work energy equation or energy balance, right? So the first one is based on free body diagram. So we need to provide all the force acting on the body is part of F1 and F2. right? So we have the weight of the body, and then we have a force, and um, most probably the body when it moves. So there is a force acting normal to the surface, and then we have the spring force. So this is one method, right? So we need to solve all the force component, and then from that we can get solutions. And the other one is using active force diagram. In this case, we isolate the spring and make it as a body, a single body with a mass, right? And our system is subjected to for only two force there, and then we need to evaluate about the 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 earlier position to the final positions. And then if you look at this diagram, we have a general equation there. Um, we say that the work done, the work, the net force, the net work. I mean, actually the change of kinetic energy plus change of um, potential energy. And then you can look at the value of E there. State that the total energy uh, actually in dynamics called total mechanical energy of the particles. So it's include the kinetic energy and the potential energy. So actually this definition is consistent with the thermofluid engineering. Right. This is another component of potential energy since you mentioned about the spring force. Right. So if you look at the equation here, um, the similarity with the gravitational potential energy. So for spring, we call it elastic potential energy, and the definition is half kx power of 2. The lower limit will be x equal to 0, the upper limit is x. And the work done by the spring force uh, is having the same definition like potential energy. We have the final x values, and we assume that the spring stiffness, which is k, remain constant during the motion, and then we find the work associated with the spring force, which is U12, is minus the elastic potential energy changes. I think in the book, um, instead of using total the changes of elastic potential energy, the author used the work done by spring force, or in thermodynamics we call it changes in the potential energy, the elastic potential energy. Right, this is a work associated with the spring force. So using the the dot product of force, spring force, right? Spring force is minus kx, right? And the position vectors, right? So we need to know about the position vectors in this case. And the lower limit is the initial values of x. Let's say we have a one directional motion, and then we can obtain that the work associated with the spring force is minus the work done by the spring force, right? So in spring you have what you call undeformed position when there is no load, right? So if you are pulling, for example, in this figure we have a cart with two wheel. If we are if the cart is moving to the right, so we have a spring force that always try to pull it back to the undeformed position. And if the car is moving to the left, so the spring force is always acting opposite to the motion, so that the body come back to the undeformed position. So, and the bottom graph showing you about the definition of the spring force. If you have force which is varies linearly with the distance that the car is traveling, so we find that the gradient of that chart tells you about the spring stiffness. Right, so we have another concept here. So we have a work associated, we already covered work associated with the weight, work associated with the spring force, and then work associated with the external force, right? So in all these three work associated with the force, right, they are using the same definition, which is uh, the dot product of F with the displacement vectors, right? So the particle can move either in rectilinear motion or in curvilinear motion. So if we look at the general motion, curvilinear motion is more general, right? So for the rectilinear motion, if the system is work in x direction, so we need to know about the position vectors, right? So we need to know the origin of the vectors so that we can evaluate the amount of work associated with the external force. And then we have this curvilinear motion. In this case, we are not using a coordinate system like x or y, but we are using the coordinate system based on normal and tangential, right? So our coordinate system is along the tangential motion along the path, and the coordinate is we use is ds, and all the forces that acting in the tangential direction, we call it ft. So in this case, we are if we have some knowledge about the kinematic properties, for example, accelerations, then we can evaluate the work associated with the external force. And in this case, we need to know about the acceleration vectors. Similarly, you can apply to the rectilinear motion if you know the x dot, double dot, the acceleration in x direction, so we can apply that equation to the rectilinear motion.